the fifth lecture on rigid body dynamics. In this lecture, we shall continue our discussion on the rotation of rigid body about a fixed axis. And in the last class, what we have obtained is that the angular momentum, if we take the component of angular momentum along the axis of rotation, then it is given by this, and the torque as I and alpha, which can be written as ddt of ln, and the kinetic energy, rotational kinetic energy, can be written as half I n omega square, and the work done in displacing the rigid body by a small amount d theta is governed by nn d theta. This was the outcome of our last lecture. We apply this theory to such a system. The system comprises of a cylinder of radius r. We have a cylinder of radius r. A rope is wrapped over it, and the cylinder is free to rotate about a horizontal axis. The axis of rotation is the axis of the cylinder itself. And a mass hangs from the string. So if we consider the T be the tension on the string, then torque on cylinder, N is equal to T into R, because T is the tension times R is the resistance. So this is this is equal to I alpha, where I is the moment of inertia of the cylinder, and alpha is the angular acceleration. So this is tension, radius of the cylinder, moment of inertia of the cylinder, angular acceleration. So if we come to the motion of the linear motion of this, the force on mass, as it is being acted upon by an inertial force m into acceleration a, which is taken to be positive in the downward direction, and it is mg, the force, minus the tension T. To replace this T in this equation, we write T is equal to I alpha upon R, and we write I A by R square, where we have written A is equal to alpha R. And linear acceleration is alpha times as R times angular acceleration. So if we replace T by this relation, we get I A upon R square. Sorry. This is mg minus I A upon R square, or A is equal to 1 plus I by mr square is equal to 0, or the acceleration is given by 1 plus I upon mr square. This is the acceleration of this particle. Now we extend the theory to a situation where the axis of rotation is in translational motion. That is, a body is rotating about an axis whose direction is not changing, but the axis is in motion. The classic example of this category is a cylinder rolling down an inclined plane, where the cylinder rotates about its axis, about its own axis, and the axis is in translational motion down the inclined plane. So motion of a rigid body where the axis of rotation is in translational motion. That is to say that if we consider this is the space fixed frame S, and we have a body fixed frame S prime, then S and S prime remains parallel all along, provided they were coincident at t is equal to 0, and the axis of rotation has a fixed direction. In this case, if we consider the position of a particle, this denoted by r in S prime, then this is the r center of mass coordinate, and this is the ri prime. So this is the position in S prime, this is the position of center of mass, and this is the position of the ith particle in SR frame. Now, coming to the angular momentum. Angular momentum L is summation over I, Li, which is summation over I, Ri into Fi external, this is MVR. If we replace R, and this expression gives us Vi, the velocity of the ith particle, is the velocity of the center of mass, plus the velocity of the ith particle with respect to the center of mass. So this can be written as R plus Ri prime cross Mi capital V plus Vi prime. Now this will give rise to four terms. First term is R times, only I dependent part is this, so this is M into V, plus the second term, this multiplied by this, so this is R cross summation over R, Mi Vi prime. Second term is this, third term is this, summation over Mi Ri prime cross V, and the last term is summation over Ri prime cross Mi Vi prime. By the definition of center of mass, this is 0 and this is also 0. Because we define center of mass position as in terms R is equal to summation over Mi Ri. This is the center of mass. So if we take the moment of the mass with respect to the center of mass is 0, and as a consequence this is also 0. So this is the moment of inertia of the central, angular momentum of the center of mass, and this is the angular momentum of the rigid body with respect to the center of mass, where LCM is equal to R times this and if we work on the component form, then Ln is equal to LCM, its nth component, plus L prime, its nth component. This is one important relation. If we take n to be along z-axis, so this Lz is equal to LCM z, L prime z. So this is one relation. Now coming to the torque. So torque N is equal to Ri cross Fi external summed over I. We write it as summation over I, capital R plus Ri prime cross external. So this is two. One part is R cross Fe plus this is the torque. If E is the total force acting on the system, so this is the N of Cm plus N prime, where LCM is the total. It is as if the total external force acts on the center of mass of the system, and this is the torque which acts at it. And this is the N prime is the summation over Ri prime times Fer. This is the torque of the external force acting on the individual particles with respect to the center. With respect to the center of mass. In the component form, this equation reads as N prime. Now we know another relation that this N is equal to ddt of Ln, which can be written as ddt of, in terms of LCM n plus L prime n. So if we write this, we get it in dd of LCM n dt plus dl prime n dt. This obviously is this part, and so we find that N prime n is equal to, that is the torque, the nth component or the component of the torque acting along the axis of rotation with respect to the center of mass is equal to time rate of change of a component of angular momentum with respect to the center of mass. So this is the relation. If we calculate the kinetic energy, we will have the kinetic energy comprises of two parts. So if we go to the calculation of velocity, this, and if we calculate kinetic energy from this consideration, well, the kinetic energy TR will have two components. One is the translational kinetic energy, other one is the rotational kinetic energy. So this is the total kinetic energy. This can be written as half mv square, that is the kinetic energy of the center of mass, and this is half I n omega square, where In is the moment of inertia along the axis of rotation in CM frame. So the CM frame has been denoted as prime frame. We shall now apply this theory to a cylinder rolling down an inclined plane. So we have a cylinder which rolls down an inclined plane. The inclination is, say, r phi is the inclination. The cylinder starts from point A and comes to point B, and this height is h. So if we consider the cylinder over here, then it starts rolling from this point A. So at that point its energy was entirely mgh. This is the zero level of potential, so this is the entirely potential energy, and it has no kinetic energy. And as it comes at a distance, say over there, or at a height this, if it is be over there, so let me write it capital H. So this is capital H, and when it is over there, it is at a height h, the potential energy is mgh, this much, and we have kinetic energy half mv square. This is the velocity of the center of mass, and we have half I omega square. I is the moment of inertia of the cylinder, and omega is its angular velocity. We know the field relation, that is I is equal to mk square, the radius of gyration. We know the relation between V and omega. V is equal to omega r, where r is the radius of the cylinder. And if we put this expression in here, we can find out the expression for angular velocity, linear velocity or angular velocity. This problem, here we have solved this problem from energy consideration, assuming the cylinder to be over here. The same problem can also be solved from from force consideration. The weight acts vertically downward, and it has a component in this direction. This is mg sine alpha, which acts downward, and the frictional force acts along this direction. So if the particle slides down with an acceleration a, then mg sine, so this is psi minus f is equal to ma acceleration. And if we consider the rotational aspect of the body, then the torque produced by the frictional force is F into R. This is equal to moment of inertia times angular acceleration, and this can be written as I alpha by R. IA by R, because R angular acceleration and linear relation is this. If we use this expression to eliminate it, we will end up to the same result. So by this, we end our discussion on the rotation of a rigid body about a fixed axis. We have considered two situations. Once where there is no translational motion of the axis of rotation, that is, the body is fixed at a point and is executing pure rotation. And in the second example, we have considered a case where the body has simultaneously rotational and translational motion, but we have put a restriction on the direction on the rotation axis. That is, we have chosen the rotation axis such that the axis is in translational motion and it has no rotation. That is, the axis of rotation has fixed direction, it only has an acceleration, translational motion. In the next class, we shall consider the most general case of a rigid body motion, that is the motion of, the most general rotational motion of a rigid body, that is a rigid body rotating about a fixed point. When the rotation takes place about a fixed axis, the rigid body, as we have pointed out earlier, has only 1 degree of freedom, and this is denoted by the angle of rotation about the axis of rotation. But when a point is fixed in a rigid body and the body can rotate about any axis passing through this fixed point, so the body will for such a rigid body, it has 3 degrees of freedom. All the 3 degrees are assigned to the rotational motion, and as a result, the axis of rotation is not a fixed axis. The axis of rotation may have any orientation in space. Only restriction imposed on it that it should pass through the fixed point of the rigid body. So that would be taken up in the next class.